Hello. Yes, it is on.
Say one more thing.
Intersections with varieties.
Perfect. Thank you.
All right, next we have Harald Helfgott's third lecture.
Very well. So, again, we are in a group G, an algebraic group. We have a subset A of G. Of course, if we want to write things correctly, we write G of K, that is the K-valued points of the group. And suppose that A doesn't grow rapidly. That's the most interesting case. That's what we want to study. When can it happen that a set doesn't grow rapidly? What properties does such a set have? So in particular, if you have that V is a subvariety, such as a curve or a plane, what can we say about the intersection of A with V? And I think I already mentioned it once, that we will start by giving upper bounds. So first of all, I should review a bit of language. I suppose most of you have seen varieties before. Can we take a poll? Who believes very well. All right. So actually, there will be no schemes. No schemes will be heard in the course of this proof. We don't really even need veil foundations, in the sense that for us a variety will always be given by some polynomial equations in affine space or projective space, right? When we say that a point is generic, we just mean that, so X is generic. Well, in fact, it will be just a matter of speaking, because we don't really need to give a strict meaning to this phrase. We just have to say that a property P holds generically in W if there exists a subvariety of positive codimension. So W is a variety like V, and it's of positive codimension, and outside the variety P holds. No? So generally, if you have a special condition that is fulfilled, say only on a curve or on a plane in something of bigger dimension, then we say that the negation of that property holds generically. Now, well, let us use this property right away, and you could, well, so by the degree of a variety of dimension, of variety V, of dimension, there's some noise coming from somewhere. At any rate, of dimension R in, say, P to the N, or this is the number of points of intersection of V with a generic plane of dimension n minus r. No, so if you have a curve, right, it's a curve on the plane, then you take a line, and unless the line is extremely stupid, like a tangent line, then the number of points of intersection will be constant, and that's the degree of your curve. The number of points of intersection defined over the algebraic closure. That's understood. So here's an example of a use of generic. Of course, we are implicitly talking about the variety of all planes. That's given by a Grassmannian. So it can be defined as a legit variety, well, in this very naive sense, even over Pn. But we will say generic quite a lot of the time, and you will understand what I mean. All right, so that's the degree is then given by the number of intersections with a plane. But what happens when you intersect two curves or two varieties? So if you have a curve, so Bezout's theorem, if you have a curve of degree d1, and you have another curve of degree d2, then I'm actually not writing, well, I haven't drawn all points of intersection, but the number of points of intersection of C1 and C2 will be at most d1 times d2. In fact, it will be exactly d1 times d2 if you are working with generic curves, or if you are counting points of intersection with multiplicity and you don't forget the points at infinity and so on. But all we care about is really the inequality here. And it turns out that this you can, well, you have this in general, because in general, and this is a generalization of Bezout's theorem, you're going to have that if, say that V1 and V2 are irreducible for simplicity, or if not irreducible, I mean, the degree here, it was really defined for an irreducible variety, but you can extend the definition to any pure dimensional variety, that is, to a union of irreducible varieties of the same dimension. But let us say V1 and V2 are irreducible, then I claim that the degree, the sum of, so V1 intersection V2, this will be a union, a disjoint union, well, not disjoint, but a union, a non-redundant union of irreducible varieties. And then the sum of the degrees will be given by at most d1 times c2, where d1, di is the degree of vi. Now, and this will be important to us, not so much the exact form actually, but it's important to us that we are able to control the degrees of intersections, the degrees and complexity of intersections. Notice how J itself is being bounded here, because this means in particular that J is at most d1 times c2. So you cannot have just two, if you know the degree, or you have bounds for the degrees of two varieties, you cannot have an intersection that, you know, decomposes into a myriad varieties. There's some bound on the complexity, on the number of components and the degree of each of them. All right. Now that we have that, let me talk to you about escape from subvarieties. So what do we mean by escape from subvarieties? I have told you that you can think of varieties of positive codimension, that is of dimension less than that of the ambient space or of the ambient variety, as being in some sense special. Now, it's very important to be able to escape from special conditions. You know, you have a set A that generates G of K. So, and it may be that you're really unlucky. All your points in your generating set A are special, but you should be able to generate quickly points away from this special variety. So what do we mean by that? We are given, so first of all, G acts linearly over AN. We are giving a group like that. It need not be algebraic. Then you have a subvariety, a proper subvariety of AN. Since AN is irreducible, W is of dimension at most n minus 1, so positive codimension. You have also a set A in G, a set that generates G, and for simplicity, as usual, we assume that the inverses are in there too, and the identity is in there. And you are given a point X in AN, such that AN of K, but I will not bother, such that the orbit is not contained in the variety. I could put k all over the place. So nobody is wondering what I am doing put in parentheses, right? I just mean the points defined over k as opposed to over the algebraic closure or a subfield of k or whatnot. It doesn't matter for our purposes. And well, it was over the complex numbers. Well, I will answer questions about the history of the result the next time the microphone runs out of batteries. So, because the orbit is not contained in the variety, you know that eventually you will escape from it. But what you want is to be able to escape from the variety quickly, that is in a bounded number of steps. And you can, in a number of steps that is bounded, only just in terms of the degree and dimension of a number of the components of W. So there exists constants, Kc, depending on what you might call the complexity, that is a number, dimension and degree of the components, irreducible components of W. By the components, I just mean the irreducible pieces it's made out of, such that there are at least, well, there's at least one, and also there's at least basically a positive proportion of elements g of a to the k, such that gx is not in the variety. Cool. So let me give you first a proof that will feel very cowardly, because I'm going to give you a proof for a really, really special case. So proof for W linear and irreducible. But as we will see, to the extent that I'm oversimplifying things here, it will just be from the fact that it's irreducible. The linearity is not, it actually doesn't change matters that much. So W is a plane. Can you escape from a plane in a bounded number of, yes, linear variety of some dimension? Can you escape from that in a bounded number of steps? Well, first the base case, dim. So I will actually just focus on showing that there's at least one element, and I can leave this part as an exercise. So there exists a G in AK, but it flows naturally from the proof that there are actually a constant times A such elements. So the base case would be dimension W equals 0, and that's quite easy, because then W has to be a single point, right? So either, yeah, well, that's pretty basic. So since Gx is not in W, we have either X is not in WK, or, Gx is not, so X is in, well, X is pretty much the point in WK, and Gx is not in X, so Gx is not. Gx not in WK for some G in A. Yeah? Because if all of A were to fix G and G were on the variety, then you would never escape from the variety. You would never escape from that single point. obvious. So that's a base case, fairly silly, like most base cases. So, case Wm, m plus 1, and we have already done m, say. It's proof by induction. Then what do? Well, you take W. If GW were equal to W for every G in A, you would have GW equal to W, right? Because A generates G. But in that case, the fact that Gx is not contained in W implies that X is not in W to begin with, so that you don't need to escape, you're already outside the variety. So you have that GW is not W. But if you have a plane and you have a displacement of the plane that is not the plane itself, then the intersection is of lower dimension. No, so it has to be of dimension at most m. And we are assuming that we are done with dimension at most m. So you have that there is at least one way to escape from GW intersection W. So K bounded in terms of the dimension in terms of n. So such that A1 AK times X is not in GW intersection W. But what does that mean? That means that in just one more step we are able to escape from W itself. Because if A1 times AK times X is not in the intersection, then we have that either A1 times AK times X is not in W, or if this is in W, then it cannot be in GW. But so G inverse A1 AK times X is not in W. But G is in A, so in either case, in G inverse is in A as well. So in either case, we have escaped from the variety W in K plus 1 steps. All right, so the generalization to W not irreducible, it's basically, you better do it yourselves. You have some hints in the notes. It's basically accounting. I mean, you have several planes to begin with, and then you have, that the number of intersections may be growing, because if you have two planes and you displace them, you might get 4 lines as intersection. But you see how that is being controlled, the number of components. So we went from 2 to 4. The number of components has got squared, but it can never get more than squared. So it's under control. You have to be a bit careful in case you have varieties with components of distinct dimensions. You have to do the accounting correctly, but you can see how the descent works. And now to W general, so not necessarily a plane, just any variety. Well, that's the easy part. Once you have got the accounting done right here, the generalized form of Bezout's theorem allows you to keep track of the degree of your things. We never really use the fact that we're dealing with planes, after all. We're just using the fact that a plane intersects a plane at another linear variety. But a variety intersects another variety at a variety, and its degree is bounded by the we use generalized Bezout, which in the form that I know it is due to Fulton and McPherson. Very well. All right, so escape is a very useful tool. We will see how to use it. Now, we will use it in part to prove a statement that could be seen as a stronger form of escape, in the sense that we will show not just that you can get out of a variety, but that the intersection of A with a variety should actually be pretty small compared to its dimension. Very well. So dimensional estimates. I don't want to say that any estimates are dim. It could be misunderstood. Very well. So by that we mean, so the most general kind of statement we have is when you have that A generates a GK, that itself could be softened, but A generates GK. G is a simple algebraic group, linear algebraic group. Is my handwriting always clear? Yes. Very good. And V is a subvariety. Then I claim that the intersection of A with V is at most a constant times, well, you put in the inverses and the identity, and you raise it to the kth power, which may or may not make much of a difference. And this is dim V over dim G. So in particular for sets A that barely grow and that contain their inverses and so on, the size of this is basically the size of A. And here, by the way, the constant depends only on the usual things: number, dimension, degree of components of V. So, what does this mean intuitively? It means that a set that grows slowly is extremely regular from many different perspectives, from just about any given perspective. So if a set grows slowly, it has to be some sort of ball, because if you think of it as being three-dimensional, dimension of G equals 3. Take a variety V of dimension 1, so you stab the ball, and the intersection will be the cube root, at most roughly the cube root of the volume of the ball for any variety. Or if you intersect it with a plane, it will be the volume to the 2/3. No? So sets that grow slowly are extremely regular. This is what the statement is telling you. Well, just a tiny bit of the history. So actually, when I was first working on the subject, I was working with A general. So not that it matters, but I was working with A general and V special, in the sense that my proofs tended to be ad hoc. It was always the same idea, but I had to do some ad hoc work. But it turns out that there were older results in the literature, though it was in an unpublished preprint by Larsen and Pink. And they were funny. So this is another instance of a case where some results in group theory that were proven for subgroups are true in general, because they were working with a subgroup of G. But G and V general. And then this was proven for A general and V general by two teams of people. So working from both ends, really. So Bruyère-Glintau and Piver-Sabo. But the idea of the proof is basically the same. You can state it in terms of groups, or, as we will see today, it can help matters to work over Lie algebras, as I was doing from the beginning. So G, A general. But at any rate, you have this very simple and general statement. And the proof I will give today, well, we will prove it for just for the varieties we need in SL2, but I'm going to give you a proof that generalizes easily. That's the philosophy of the course here in general. So what do we do? First, actually, let me give you a proof of a statement that I had back in the day, but in 2005, a statement that we will not actually need that precise statement, but as it is extremely concrete, it helps give the general idea. So we will need later to give a lower bound for the number of points on the maximal torus. But I will give you now an upper bound. So I remind you, so we already saw maximal tori last time. But let me remind you, well, now we are working in SLN. In SLN, a maximal torus is just, well, in general, a maximal torus is just a centralizer of a so-called regular semisimple element. But what does regular semisimple mean? In SLN, it means having having n distinct eigenvalues. No, so it has no repeated eigenvalues. Very well. So in particular, you can always you should think of a maximal torus as just being the group of diagonal matrices, because that's what it becomes after conjugation, by an element that might be defined over the algebraic extension, but still. So, lemma, let G be SL2 over a field K, and A is a finite set of generators, well, containing the inverses and the identity. And then I'm going to sketch for you a proof that the intersection is at most, well, what it should be, a to the 1/3, a to the k to the 1/3, where this k and the implied constant here are absolute. So I'm going to proceed in the most primitive way possible. As I said, when you want to prove an inequality, much of the time, to prove an inequality, it's enough to prove an injection. And if that doesn't quite work out, then you prove that a map is almost an injection. It maps at most, say, 5 things to a given point, and then you have a bound with a factor of 1/5. So, you can write these T's as diagonal matrices. You can also assume that the field is larger than a constant, and so on. So let us start with a G, A, B, C, D, pretty much any G, but we will need that none of the entries be 0. Now we are guaranteed that there's such a G in A to the L. Why? Why is there such a G with non-zero entries? I mean, all of its entries are non-zero. Why is there such a G in A to the L? Exactly. Because having the upper left corner equal to 0 defines a variety. Well, having some entry equal to 0, it's a union of irreducible varieties like that. So it's a variety in our language. And you escape from that. You could be very unlucky and have that all elements of A have at least one non-zero entry. But after you multiply it by itself a few times, you escape from that variety. You get an element that is generic in this sense. So the idea of escape from variety should be clear now. So if you ever need an element that is not evil, where evil is a very special condition, then yeah, there is an element that is not evil in A to the k. Where by special I mean being as a variety, satisfying an equation. Very well. So now consider the map, a map from T of k, T of k, T of k to G of k, a map given as a product. So it's going to be, say, x times a conjugate. Could define it otherwise, but say this is good because it's a product of inverses and elements of the entries. And then, very well. Excuse me. So this is, the map takes x, y, z to that. Very well. Now, suppose, proof by wishful thinking. Suppose I had a ham I would make a ham sandwich. So suppose phi were injective. What would we have? As I said, well, it's the simplest idea in the universe. So an injective map has image size equal to domain size. So you have A times so it was good that this map was defined by a product, and it was good that G is in A to the L. And so, well, and of course this is A to the to L plus 3. So L here is a constant. Escape from similarities guarantees us that. So that this would be good, right? This would give us a result right away. This would give us the intersection of A with T of K is at most the cube root of A to the 12 plus 3. Now, phi need not be quite injective, but it's enough for phi to be sort of injective. What do I mean by sort of injective? Now, just by an exercise in multiplying matrices, you get that for, say, X is, R inverse. So if you take the image of phi x, y, z, and then you take the pre-image of that, you take the set of all points that get mapped to that same point, you obtain that this has at most 16 elements, provided that, well, some very special conditions. This is a minus. But so A, B, C, D are fixed. So these two special conditions are fulfilled. I mean, these two non-special conditions. I mean, special means equal. These two non-special conditions are fulfilled at all but 4 points. There are just two solutions to S inverse minus S equals 0, and two solutions to the second equation. So this is true for all but 4 points. So we obtain then that phi of 80. So this is just high school algebra. I will not do it here because you would be very bored, and because we are all old and hence dull. But let us focus in on concepts. So you obtain what? It's the same thing, no? It's just, instead of an equality, I have an inequality. So I have a factor of 1 over 16th. Here I subtract 4 points because there could be 4 exceptions. Yep. And so either you have that AT over K, AT intersection K is less than 8, and then the conclusion is trivial, or it's greater than 8, and so subtracting 4 in the worst of all cases halves it, and so you have that A intersection TK is at least 1 over 32. No, it's at most 32 times A to the 12 plus 3. No, so it's almost as good, and you're done. Really, that was it. For this particular group and this particular variety. But so there's only one bit that doesn't generalize so easily. It's a bit where I said it's high school algebra. No, because high school algebra, unfortunately, it's something you have to do with your hands for any particular variety. And as soon as you get to 3x3 matrices, things start getting really, really messy. And you wish you had been, more highbrow to begin with. So what are we really using here? So let us abstract what was the basic procedure. in general, say, let's work with the case of dimension of v equals 1 at first. So let this sort of statement with 1 over the dimension of g instead of 1 over 3, 3 is the dimension of this g, this sort of statement is true not just for t, but for any one-dimensional variety. And what is the strategy of proof? So you define phi from the product v, so this is r times, where r is the dimension of g. You define a map like that, and let us say that it will send v1, vr to v1, g1, v2, g2, why not, gr minus 1, vr. And then show that there exists, g1, gr minus 1, such that this map is almost injective. Meaning, for, say, v1 not in W, where this is as a variety of v cross v of positive codimension, you will have that, as before, the pre-image of the image has dimension 0. So it's made out of points, discrete points, and the number of these points is bounded by the degree of the variety, which is controlled because if you take images and pre-images of something whose degree you know, using maps whose degree you know, the degree of the resulting variety is bounded. So once we have that, then exactly the same argument works. So first of all, there are such g1, gr minus 1 in a to the of 1 by escape. So why is that? Well, I might as well tell you now. The way I really like to see things is I like to take, derivatives, tangent spaces, and you can do that over any field, not just over the reals, and things work almost pretty much exactly the same. So, in fact, when we are defining a map phi like that works in this way, what you are doing is really so we show that phi is almost injective by showing that d phi, the derivative map, is non-singular. So, in particular, injective for X generic. But that itself, the fact that this is the case for given G1 up to GR, that itself defines, that it itself is the same as saying this tuple of points is not on a certain variety. And by showing that there's a tuple of points, G1, G2 up to GR minus 1, for which this works, you're showing that that variety is not the variety of all Gs. So the good things, the good Gs, are the ones outside a variety. There exist Gs that are good, hence the variety has positive codimension. And so you can escape from the variety of bad Gs. This is true for G1. Now, this is all given by equations. Now, and once you have such G's in A to the O of 1, exactly the same argument works. You basically don't have to change a dot. You just have, you don't have 16, 8, and so on. You just have some constants that depend on the degree and dimension of things, but that's it. So the question is really then, well, can we find G's such that this map is generically non-singular? Well, let me tell you a bit more about groups and their dimensions and their tangent spaces. So people love to draw curves even when they are working over finite fields. I'm no exception. That's, of course, sort of absurd, except it works. I mean, curves, anyhow, are really solutions to equations. What we draw is really some sort of molecules that we leave on paper, and they are supposed to give us a picture. So what we have is, you have an linear algebraic group, or you can have a slightly more general notion, really. So over K, so for K finite, we speak of G being a group of Lie type. Well, though this is a somewhat more general notion, because you can have funny twists and whatnot. Whereas for K infinite, or for K equals to R or C, we would just speak of a Lie group. Right? Now, what happens with Lie groups? How many of you are familiar with Lie groups? Everybody's familiar with everything. Well, sort of. All right, so you have that, the Lie group, you can see it as some sort of surface or variety over R. And then you have the identity, and at the identity, you take the tangent space, G. And the wonderful thing about the tangent space is that, well, G was not just a variety, it's a group. And the wonderful thing is that G inherits some of the structure of that group. And that's the case whether you are working over the reals, the complex numbers, or a finite field, or an arbitrary field. So what is the sort of structure that G inherits? So you have the map from G cross G to G. It's the map bracket. It sends G and H to GH, G inverse, H inverse. Right? And now you take the derivative of this map. So you don't need to you cannot take limits over finite fields, but these are things given by polynomial equations. You can take the derivatives purely formally. So this is valid over any field. So the derivative of this map at E, or at E comma E, this is then a map from G cross G to G, which we also denote. Well, this is what really should be denoted by a bracket. This is a usual commutator bracket, and there is a Lie algebra bracket. Very well. All right. And G is a Lie algebra. It's a funny algebra. It's a thing with a bracket. So it's a vector space with a funny bracket. Obeying certain rules. Let us not go into this. Let me just define the most basic concept. So G here is a Lie algebra. So it has this bracket. And an ideal I of a Lie algebra G is a subspace I of G such that when you take the bracket of any element of G with I, you get something inside I itself. Very well. So, in particular, and it's quite easy to see simply by taking the derivative first with respect to one variable and with respect to the other. If a subspace, so I'm going to define as well an action of G acting on G Gothic. So how does this act? This is the derivative of the conjugation map. No? So add G from G Gothic to G Gothic is a derivative at E of the map H, G inverse, of the conjugation map. So at G is basically conjugation. You conjugate an element in the Lie algebra by an element above in the Lie group. Very well. And it's easy to show that you can actually define the bracket as a derivative of a G, so the derivative of a derivative. But if a subspace, it follows directly from that if a subspace I is invariant under at G for every G, then I is an ideal. And we say a Lie algebra is simple if it has no ideals other than 0 and the entire thing. No proper ideals. Very well. All right, so simple, that suggests a link with simple groups of Lie type. So, well, it's a simple group of Lie type is just, as usual, a group of Lie type that does not have normal algebraic subgroups of dimension greater than 0 and lower than the whole dimension. So, over R or C, G is simple, or we will say almost simple, meaning no, as I said, no normal algebraic. So it could be really have a really stupid normal subgroup consisting of 2 points, say, but never mind that. To give an example, of dimension between 0 and dim G. So this is G is almost simple if and only if G is simple. So one direction is very easy, this one. Then this one is a bit harder, though over R and C it's not particularly hard. Over K you have to be careful, because when G is almost simple, so this is implied by this would be implied by the simplicity of G, and that's not hard at all. But here this is sort of true. This is true only in non-nasty characteristics. So for car not too small. In particular, for G equals SLN, you need the characteristic of the field not to divide n-1. So, well, in SL2 you have no problem whatsoever. In SL3 you have to be careful with characteristic 2, and so on. It's a minor annoyance. I think, well, you don't have to work over the Lie algebra, but I prefer to work over the Lie algebra. I think it makes life much nicer. But given that, knowing that we have to work with a simple Lie algebra, that's not exactly given for free, what are we going to do? So we want some sort of skewness. I have 1 minute, 20 seconds left? Well, is that really true? At any rate, we want, so let me prove something very quickly. So you have G, it's almost simple. We want G such that G is simple algebra. And these are irreducible subvarieties. Then we want to show that there exists a subvariety W such that for all G not in W, VGV, this new variety, or I should really write as a risky closure because there might be some points missing. This has dimension greater than V. So I have a variety V, and I have another variety V prime, and V prime might be contained here, but I want to know that you can displace it by some G so that it gets out of V. Unfortunately, here I must finish, but I will just give you the idea of the proof, which is extremely simple. So basically, the point is that, as we can assume without loss of generality that V and V prime goes through the identity, otherwise we just shift them. And then you're looking at two subspaces, V and V prime. And you win, we will win, if you showed, so we must show that there exists a G, and that will be enough. Then it will be evident that it's really a generically true condition, that there exists a G such that GV prime, G inverse, is not contained in V. These are subspaces. Suppose not, then the space generated, the space spanned by all, so this is add of G applied to V prime. So space spanned by all G, V prime, G inverse is an ideal, it's invariant under conjugation, contained in V of dimension greater than 0, but that contradicts simplicity. So you are done. That's basically it. So there exists a G such that this is true, and then when you look at what it means for the dimension here, for this not to be contained in here, it's always about minors not vanishing. So it is about not being in a subvariety, and if you show that there's at least one good point, it means that the subvariety is of positive codimension, since it lives in something irreducible. So this is really the key step, and well, we will leave the rest for tomorrow.
Questions for Harald?
Yes.
Just a tiny correction to that last proof. In the last step there, I think you use the fact that V prime has dimension at least 1.
Yes,
so
yes,
you need
I
to
should
include
have
that
said
in the
that.
statement.
Yes, otherwise it would be obviously dramatically false. So dim V prime. Thank you.
Great.
That's it.
Great. Let's thank Harald again.